being a little ahead of time because I want to make sure we give Peter Lindstrom plenty of time to present his paper. He spoke last year and gave a very impressive talk on the fundamental principles behind designing a new number system, and he has, I think, an equally fascinating talk about how do you really represent real numbers with bits. Peter runs a group at Lawrence Livermore National Lab that does mathematical computation, and a really interesting team. It comes up with some fantastic stuff. So, Peter?
Thanks, John. Okay, yeah, so as John alluded to, I gave a talk at CoNGA last year, and what I'm presenting this year is essentially an extension of what we presented last year. So some of you, if you were here last year, might recognize some of these slides that I'll be using in this presentation. So I wanted to start with a simple exercise here. I'm thinking about an integer number between 0 and 99. Anybody care to make a guess? No one? 50? Wow. What a coincidence. Right. So, you know, everybody is pretty familiar with binary search for integers. And in this binary search, what we're doing is essentially just making comparisons, right? And the outcome of each comparison corresponds to a 0-bit or a 1-bit, depending on whether the number was larger than or smaller than our guess. All right. Slightly more difficult exercise. I'm thinking about a number between negative infinity and infinity. Any guesses?
0.
Ah. Yeah, it kind of makes sense, right? You know, you want to know if it's a positive number or if it's a negative number. Okay, let's take another guess. Suppose that we know that it's a positive number.
1.
Wow, you guys are good. All right, so yeah, you know, it kind of makes sense. You know, half of our numbers might, you know, be between 0 and 1, and half of them might be between 1 and infinity. But now the question is, where do we go from here, right? What's our next guess going to be? So suppose now that we know that the number is larger than 1, but it's, you know, in this unbounded interval, right? So what should our next guess going to be? And, you know, one answer to this question was made back in 1976 by Bentley and Yao, where they presented what's called unbounded search. So the idea in unbounded search is that we start with a number 1, and then we create this monotonically increasing sequence of guesses until we've bracketed the number. So for instance, you might just continue doubling your previous guess, and at some point, you're going to bracket the number that we're looking for, number x, between a sub I and a sub I plus 1, right? And at that point, we can continue with our binary search to actually encode the number. And you can show that you can actually encode any arbitrary real this way, assuming you have enough bits of precision to do so. Okay, so what we're going to do here is that, you know, we're going to, you know, develop this sort of sequence of monotonically increasing guesses, which works well for numbers above 1. For numbers between 0 and 1, what we're going to use is just a reciprocal of that sequence of guesses. And of course, we want to represent negative numbers as well, right? And we can just append, you know, or prepend assigned bits in order to do so. So this allows us to encode arbitrary numbers. Then the next question is, what makes for a good bracketing sequence? You know, I mentioned that we can just double the previous number, but, you know, is that the best we can do? So what might not be a very good bracketing sequence? And I would argue that IEEE 754 makes some very, very curious guesses. All right, it guesses first whether the number is above 0 or not. Makes sense. It then guesses that x equals or is greater than or equal to 2 if it's above 0. Not 1, but 2. And that roughly corresponds to sort of getting the sign bit right for the exponent. Now, the next guess, if we're above 2, is 2 to the 513th. Now, just to get an idea of how large a number this is, suppose that we were to measure distances in Planck lengths. Okay, that's the smallest meaningful length, right? Then this guess corresponds to about 1 gogol, or 10 to the 100th, diameters of the universe. I mean, is that really the best next guess to make after 2? Well, that's what IEEE would have, right? So what ends up happening here is that we get this sequence right, 0, 2, that's greater than 2, then 2 to the 513th, and then we sort of have to backtrack, you know, all the way back here. So if our number was actually 3, then we made all these ridiculous guesses, right, until we got back to something that's more reasonable. All right, so are there better representations? Well, John has proposed POSITS as one contender to IEEE. I'm not really going to go through this slide, but just to show that, sort of the main difference between POSITS, well, there are lots of differences, but one of the differences is that whereas IEEE uses a fixed length representation of the exponent, of course POSITS use a variable length representation. So it looks something like this. Oh, that doesn't look good at all. Sorry about this slide. Something got lost in the translation here. But what this is supposed to be is essentially your standard representation of a real number in terms of a sign bit, an exponent, and a fraction, right? So POSITS and IEEE both encode these kinds of numbers. There's an explicit representation of the exponent, whereas IEEE uses sort of a fixed length binary encoding. POSITS use what turns out to be a Golem-Rice code for the exponents. And as a result of this, small exponents around 0 get represented using fewer bits, and then as you get to larger and larger exponents, POSITS use more and more bits, right? So you have this notion of what's called tapered accuracy, right? As you get to larger and larger numbers, you have less accuracy. Now, going back to 1975, Peter Elias proposed his codes, 3 different codes, as it turns out, for representing arbitrarily large integers. And once again, he separates these integers into an exponent part and what essentially amounts to fraction bits after that. Okay, so these are the 3 different codes. I'm not going to cover these in detail either. Just to point out that his gamma code turns out to be identical to John's POSITS with 0 bits of exponents. So those are 2 identical representations for integers at least. So what we did last year, excuse me, I lost something here too. What we did last year was essentially extend these ELIAS codes to the real numbers, right? So the idea is that we can represent integers, we can get, fractional numbers by just appending additional fraction bits at the end of the integer. For numbers between 0 and 1, we actually use a signed representation of the exponent, right? So that gives us numbers between 0 and 1. And then we can also prepend a sign bit to get negative numbers. And we presented this framework that allows you to model different number systems in a very modular manner, right? So we essentially have different modules that correspond to C++ templates where you can plug in, ways of encoding exponents. So we provide actually, a number of different encoding schemes, but you can develop your own, right, to do that. But there's an explicit representation of exponents. There's an explicit mapping of the fraction bits to a real number. And sort of the standard way that IEEE and POSITS do that is just by linearly mapping sign bits to a fraction. We have rounding rules, and you can play around with different ways of handling under and overflow also. But as it turns out, if you were to actually implement this, then it might look something like this. This is just the code that we provide for the encoding and decoding of the ELIAS omega exponent. All right, it's about 144 lines of code. You get any one of these lines wrong, then you've got a tough debugging problem here to deal with. So what I want to present today is a much simplified view of this and a much simpler framework for building number systems. All right, so some of you might be familiar with John's ring plot. At 2 bits of precision, these are the 4 numbers that we can represent, right? We have 0, -1, +1, and plus or minus infinity at the top here. And when you think about this, you can also think about these in terms of intervals, right? There are some numbers in here between 1 and infinity that correspond to these intervals. All those numbers get mapped there when you have 2 bits of precision. And then as you add precision, you start introducing points in between these, right? And you can think of this as essentially just bisecting intervals. Not at the midpoint, that doesn't make sense when you're dealing with infinity, right? But we're essentially just partitioning intervals into 2 smaller intervals and so forth. And we keep adding more and more bits of precision, and that's what we end up doing, right? So, as it turns out, we want to use different rules for introducing these additional numbers when we bisect these intervals. So, I like to think of these as 3 separate rules. So when we're starting with just 2 bits of precision, we will have numbers, say between 1 and infinity, where you have an unbounded interval. And then we use a special rule for bracketing the number. And as I do that, I introduce a new number. And now you'll see that we have this red region where the number is somewhere between this largest number that we can represent using 3 bits position here and infinity. At the bottom, you have corresponding numbers between 0 and the reciprocal of this largest number, right? So what we're going to do is that we're going to develop a bracketing rule up here, and then we're just going to reciprocate to get it down here. And then we also see that there are these green regions where these intervals are actually bounded, right? And we're going to use a separate refinement rule for introducing new points there. But they're essentially, think of this as just 2 different rules that we're going to show how to do it. And again, you have reciprocation and negation. All right, so in the first case, we have this unbounded search where you want to introduce a new point in between the previously largest number and infinity until we've bracketed our number. And we're doing that, again, by introducing this monotonically increasing sequence of numbers, a sub I, where a sub 0 equals 1. And the way that we generate this sequence is through a function g that we call the generator for the sequence, right? So you just plug in the previous number and you get a new number, and you plug that back in and you keep going, right, to generate this increasing sequence. So as an example for ELIAS gamma or POSIT 0, you have this. You just double the previous guess, right, and you keep going that way. Again, we have the reciprocal numbers here to generalize this to numbers between 0 and 1. And then we distinguish 3 separate cases here, okay? So in this red, it's not showing up well at all. I apologize for this. These slides, it's not the way I put them together, I'm sorry. So in the red region here, the way that we encode this value, once it's been bracketed in here, is that we have a 2-bit prefix. So going back to the previous slides here, we have the prefix 0, 1, that actually means that the number is between 1 and infinity. And then we're going to encode, we know that this number I, or this index I, tells us where we are in the bracketing sequence. And we're going to encode that in unary code. So it's I 1 bits followed by a 0 bit. And that gives you the prefix of the code, and then we're going to do additional refinement of this later and append additional bits at the end here. But this is what the prefix of this code looks like for numbers between 1 and infinity. So when we're between 0 and 1 instead, then we're dealing with the reciprocal of these numbers up here. And our code then uses a different 2-bit prefix 0, 0 to indicate that. And then we're using, instead of I 1 bits, we're using I 0 bits. So it's just a complement of what we get up here, and then some additional bits that follow after this. Then if our number is negative, then the way that we represent that is just by using a 2's complement negation of the code for the corresponding positive number, right? So we can just map all the non-negative numbers to the negative numbers using 2 complements negation. All right. So in the second case, where we're in this green region, then we have this refinement operator that takes 2 numbers, A and B, and spits out a new number, C, that is somewhere between A and B. And that's the point where we're going to decide, well, is the number below that point or above that point? Essentially corresponds to our binary search that you all already knew how to do, right? So if x is in the lower half of this interval, then we just append a 0 bit. If it's in the upper half, we once again append a 1 bit to the code. And then we just keep recursing it until we found our number. And really, for any number system, this is really all you need to do. You just need this generator g of x, that could be a simple function, and a refinement operator f of a comma b. Okay? You don't have to deal with complex bit manipulations or any of that nonsense, right? So I'm missing something here. I don't know what this should be. I apologize for this. All right, so, but just looking at, different number representations that are out there. So we have our POSITs, we have our ELIAS codes, but we can also think of new representations, right? So we have a representation that we call extended unary, which essentially just uses this generator 1 plus the previous number, right? So that generates a sequence of just consecutive integers. Now, if you want to represent a large number this way, that wouldn't be very efficient, right? You would need, n bits to represent n, essentially. But for small numbers, that might actually be reasonable. Another familiar sequence, of course, is the Fibonacci sequence that we can write as this, where phi is the golden ratio in this case, right? So that generates a slightly more quickly increasing sequence. As we get to ELIAS gamma, we double. With POSITS, we have some base b, where b is a power of 2, and that will increase even more quickly and so forth, right? You'll see that some of these representations increase extremely quickly, like ELIAS omega, where you take the previous number x and you take 2 to the x, and you keep doing that, right? That increases extremely rapidly. You can even represent IEEE single precision this way, and apologies for the formula here, I got messed up, but it's just says it's a square root of 2 to the 129 for single precision times x, right? And you keep doing that, and you actually need a special rule for IEEE because it uses a piecewise representation. But you can sort of shoehorn IEEE into this framework as well. All right, so this plot here shows what happens as you increase the precision. So for several different number representations, so I've shown IEEE double precision, which increases extremely rapidly up to the point where it sort of just flattens out, right? You can never get past this, regardless of how many additional bits you add, right? So 2 to the 100, 2 to the 1024 is actually the largest number that you can represent using double precision. Same thing for single precision, but this is a lower number and half precision over here. But you'll see that all these other representations, several flavors of posits here, are essentially unbounded, and with enough precision we can reach any number. Goodness gracious. So what this formula is supposed to show is that now we move on to the refinement operators. We have A and B, and we want to compute sort of a midpoint between A and B. And we can show that for POSITS and for the ELIAS codes. It's a very simple formula. If A and B don't differ by more than a factor of 2, then just take the arithmetic mean between the two numbers. Otherwise, you take the logarithm, base 2 logarithm of two numbers, and you recurse, and you plug those into the formula until at some point their magnitudes are going to differ by less than a factor of 2. And we call that the hypermean between the two. So here's an example where you can actually see what's going on here. 2 and 4 don't differ by more than a factor of 2, so we just get the arithmetic mean. 4 and 16 do differ by more than that. You take the logarithm, plug that in, and you get essentially the arithmetic mean between the exponents, right, which is 3. And that shows you that this turns out to be the geometric mean. For number systems like ELIAS omega that increase much more rapidly, you need to do another level of recursion, possibly several additional levels of recursion to get this to work. For logarithmic number systems, you can show that this refinement operator is just a square root of the two numbers. Okay, this is going to be interesting percent. So one question you might ask is that you have this initial bracket sequence of increasing numbers, right? How would you refine and introduce new numbers in between those in sort of a compatible way? I mean, you can just take one generator and one refinement operator in isolation and apply those, and that works. But you might want to have something that produces something that very smoothly and interpolates this bracket sequence. And the way that we're going to do that is that we're going to solve this recurrence equation where, again, a sub I equals g of a sub I minus 1, right? If you solve that in terms of, let's take this explicit example here where a sub I equals 2 to the I, right? You can actually develop a closed form formula for a sub I just in terms of I, as opposed to in terms of recurrence relationship. If you can do that, then you can actually solve for, if you set x then equals to a sub I, and then solve for I, then for this particular case where x equals 2 to the I, we have that I equals log base 2 of x, quite naturally, right? So now we've solved for I in terms of x. What we're then going to do is we're going to plug this I into what ends up being the cumulative distribution function for this number system. So for all these different number systems, you will have a cumulative distribution function that essentially says it's 1 minus 2 to the minus I. And the reason for this is that as we increase I, you output one more bit of information, but you also have the number of remaining numbers that you can represent in there. So this turns out to be true for all these different number systems. But if you have a specific I for your number system, then you plug that into this. And if we did this with this previous example, then you would have this cumulative distribution function is 1 minus 1 over x, essentially, for that particular case. And what we're going to do then is that we're going to use this resulting cumulative distribution function and plug it into a refinement operator like so, where this is essentially just a generalized f-mean of two numbers, okay? So you apply the cumulative distribution to a, to the number b, divide by 2, and the resulting fraction is halfway, or the resulting cumulative distribution is exactly halfway in between those two numbers. And then you apply the inverse function to that. Okay, and that gives you exactly the split point where you have half of the numbers being less than this new number, f of a comma b, and half of them are above that. I did not really do a great job explaining that, but it would be more clear if these equations were actually readable.
Peter, are you seeing parentheses in that bottom? After the equals that would be over 2?
Yes, I'm sorry, this should be, those parentheses did not show up
No,
either.
not the very bottom, but over on the right. You have f of a, yeah.
Yeah, they're missing it here as well, and I'm sorry, I don't know why the equations got really screwed up in my presentation. I apologize for that. But yes, so for this particular case here, what it shows you is that to get this compatible refinement operator, what we should be using is actually the harmonic mean between these two numbers. All right, so to show you, and I apologize, this is probably hard to see here on this projector, but what I'm showing here is once again this cumulative distribution function of numbers, and essentially swap the axes here. But I'm showing here the bracketing sequence, a sub 1, a sub 2, and a sub 3 for this particular example. And what POSITS will do is essentially just linearly interpolate those. So as to get a new point in between those, we would just take the arithmetic mean between those two. The problem with this is that if you actually look at the difference between consecutive numbers, then you get these discontinuities, right, as you go from one exponent to the next exponent. And that might not be something we want. We could do this somewhat naively by just recognizing that these particular numbers here can be expressed in terms of x equals 2 to the I. We saw that in the previous slide. So why don't we just put in a fractional I and see what happens, right? So between a sub 1 and a sub 2, we could use a sub 3 halves, right? By just putting 3 halves in for I, right? And if we do that, what we'll end up seeing is that we're essentially just taking the geometric mean between numbers. You'll see that this curve sort of has some kinks in it that shows up in the derivatives here, right? Where we have discontinuous derivatives. But if we use the framework that I developed on the previous slide instead, you'll plug in over here the harmonic mean instead. And what you end up getting out of this is this sort of smoothly interpolating curve between the numbers. Yikes. Okay, so I've talked about number distributions, and we're going to show that the probability density f is actually really closely connected to the relative accuracy of it. And if this was more readable, you would see that we can define our relative accuracy in terms of the base 2 logarithm of the number x times the probability density f of x here. And this derivation essentially shows here that if we look at approximations of these discrete approximations, then what comes out here at the far end is x divided by delta x. Okay, so delta x is essentially the interval between consecutive numbers, and delta x divided by x is essentially the relative error that we're making in this derivation here, right? And I was also missing something on this slide, but what this one shows here is essentially this accuracy as a function of x on a logarithmic axis here. And we're seeing different number representations here. IEEE is sort of this sawtooth looking thing that goes down all the way down here at the far end to the left. So these are the subnormal numbers over here, right? So if we were to use this natural refinement operator instead, corresponding to the bracketing sequence here, what we will get is just the logarithmic number system that gives you a much smoother sort of horizontal line here. For POSITS with 1-bit exponents, you get this sawtooth-looking thing in yellow here, right? So if we use natural refinement, you get this nice triangular shape instead. And we have the same thing for ELIAS delta, right, where you get these smoothly interpolating representations. And this is more clear probably in this plot here. We're zoomed in on this. All right, I have a couple of result slides here. What I'm doing here essentially is something very similar to what John did in the POSIT paper. The idea is that you take all the numbers that you can express in a number system, then you apply a unary operator on that, in this case, the square root of x, and you look at the relative error that you've induced in that case. And you then sort these relative errors and plot them between 0 and 100%. And instead of errors, I'm actually measuring accuracy, so it's essentially a reciprocal of error. But what you're seeing here is interesting. This gray-looking curve right here has the lowest accuracy. That turns out to be something essentially identical to IEEE, but with all the subnormals and crazy NAM representations removed, right, so that can fit into our framework. It consistently does worst. You also have a logarithmic number system that has this interesting shape, and I can explain why. I probably don't have time for that. POSITs with 1 bit fall somewhere in the middle here, and you have some of the other representations that do slightly better. Look at instead of taking the square root, we can square the number. You get something very similar. You can see that IEEE is worst. POSITs fall somewhere in the middle in here. Also for the logarithm and the exponentials, we're essentially seeing the same kind of pattern. IEEE consistently does worse. And we're not using any particular numbers that are close to 1 here. We're using all the numbers that we can represent in these different number representations. So it's sort of an apples-to-apples comparison in some sense. What we're doing here is that we're looking at the error in finite differences, where the horizontal axis here is just the grid spacing. So as we go to the left here, we get finer and finer grids. So we're starting over here, and we get finer and finer grids, and the truncation error reduces up to a certain point where roundoff error kicks in, right? So here, roundoff error dominates. And once again, you're seeing that IEEE consistently does worse among all these. That's the highest error. Here's POSITs. So we're dealing with 32-bit types in this case. POSITs will give you this. The best one here is ELIAS gamma. That's also POSIT 0, right? So it's another POSIT presentation. But these do consistently better than IEEE. Just to show you very quickly, this is the entire framework implemented in Mathematica. It fits on a single slide. You can go punch this in probably and just do a cut and paste from the paper. We have different number representations here, so each line here corresponds to an entirely separate number representation. As you can see, it's not a whole lot of code to develop a new number representation. That's all you have to do to get a new one. We have a C++ implementation of this as well. This is POSITs, the whole family of POSITs implemented in our framework. It's essentially these 2 lines of code that you have to do to define the generator and the refinement scheme. Just a quick comparison here, the sort of pros and cons of this approach. One is that we can give any new number system using 2 very simple functions that you define. So you can do really rapid prototyping this way to get a number system up and running and test it out. You can ensure that it's really correct. It's hard to get those 2 numbers or 2 lines of code wrong, right? It's very general. It supports all these other number representations as well as new ones that our framework from last year did not, because it required this notion of exponent. These new ones don't. In terms of cons, this is not the most efficient way of doing things. We're essentially parsing 1 bit at a time. So P, the precision is very large. This is not very fast, right? But you can do this to get something up and running, and then you can select a number system that works for you and then focus on optimizing that implementation. And you can use our framework to verify that it's actually correct. This natural refinement that we presented results in somewhat elaborate expressions in some cases involving transcendentals and whatnot. And that's not super fast either. It's probably not easy to implement in hardware either. And also, I would point out that we actually require this auxiliary type to do arithmetic. So we're currently using IEEE at high precision. We could go to MPFR to get arbitrary precision and so forth, right? But we can't get to arithmetic on these. All right, so on my last slide here. So we presented a very simple framework and general framework for generating new number system. We've shown that it leads to these novel representations, for example, the Fibonacci representation and extended unary. Of course, we developed this notion of connection between number systems and continuous probability distribution that we think will be useful for analyzing different number systems. You can actually plug in the closed form probability density, for example, if you're computing the sum of two numbers, you know that you want to use convolution of the two distributions to get the distribution of the sum, and so forth, right? So there are nice things that you can do with these distributions. In terms of future work, we haven't done a whole lot of work on actually evaluating these number representations. We did a lot of that last year, but these new number representations also should be evaluated in more detail. We need to answer this question of, when is it beneficial to use an exponentless representation like Fibonacci? And when does natural refinement actually pay off? And in some of our examples, that didn't seem to be a huge difference by going from something piecewise linear to something that's smoother. And then lastly, for certain applications, is there sort of an optimal distribution? You could probably actually run your code and figure out, what is my distribution of numbers, and then sort of backtrack and back out sort of an approximation to that distribution based on offering there. And I'm at the end of my talk, so if there's time, I'll be happy to answer questions. Thank you. Do we have time, Josh?
We have 2 minutes.
Okay.
Is this on? Okay, now it's on. Yeah.
Is this one on? All right. So first of all, this is really cool. I think this work is really cool.
Thanks.
Just one quick sort of question. So is it true that if you have a number encoded in one of these schemes, if you have some prefix of the high bits, those bits will always be the most interesting information?
Yep.
So okay. So you never have this question of was this part of a 64-bit float or a 32-bit float? Where does the exponent cut off?
Exactly right. So you can choose any precision. If you want to, down convert to less precision, you just drop the bits at the end.
Yeah, and it's always losing the less important information.
Yes, exactly. Yeah, you want to do proper rounding. So, but aside from that, you just throw it on the.
Thanks. Trevor Carlson, NUS. So I'm not an expert in number systems. I'm a computer architect.
I'm not either.
But I had a quick question for you. We try to build hardware. We try to build efficient hardware. And the first time when you said bitwise, and the first thing I thought was, if we wanted to implement a general number system implementation in hardware, could we do it with a bit serial implementation where we could then implement any number system by providing the information up front to the arithmetic unit in hardware, and then we can allow the unit to actually do that operation inside the hardware and optimize this.
Yeah, I mean, that would be really interesting. The one gotcha here is that you actually need to perform some arithmetic, right? So, for instance, when you bisect an interval, you need to insert that new point, you need to do arithmetic to do that. So that
well, it is an ALU, so we can maybe put some
that,
extra.
right?
We can put some extra stuff in there to do some fun stuff. Yeah, okay, that's a good point. If we have to do extra arithmetic, it was just a crazy idea, and maybe we take it offline and talk.
Sure.
I want to also say it's incredibly interesting what you're presenting. Towards the 2/3 of your talk, you hinted at the relationship between precision and resolution of precision in few numbers and the F and G functions. Is it possible perhaps to look at other statistical properties of a collection of numbers, like you might see in a simulation or so? And so there would be both a range in time and a range in spatial dimensions. And so you would get a distribution of these numbers, and then you could perhaps propagate through your functions F and G what would be the relevant qualities that you need to optimize your F and G for. Yeah, so doing it for all the numbers is less clear perhaps than picking a distribution of numbers that's correlated to particular physical problems.
Right. So F and G are very simple functions, right? So you have to be able to somehow model an empirical distribution that might exist in your code, right? And try to sort of interpolate that using these two very simple functions. But aside from that, yes, it's actually something we've done some work on. We actually collected these statistics and looked at the distributions. It's not immediately clear to me that those distributions should be exactly replicated by using these functions. You might have very, very small numbers in a simulation that you actually don't care about, that they're so small that they don't actually have a measurable impact the result itself, right?
It might be interesting to chat with some physicists that use so-called multi-point correlation functions, because these are the statistical properties of collections of numbers about which something is often known for things like fluid dynamics and so on. And then, but it feeds into something quite different, I think, namely, ultimately you're doing operations with these numbers, so what you really want to optimize for is not so directly a function of the incoming distribution, right? It's quite a tricky problem, perhaps.
Exactly. But now we can actually do this analysis using
Exactly.
these sort of
You have a handle on it. You have a machine.
Yeah.
There was nothing before.
Right.
So it's
Right.
very, very beautiful.
Right.
Yeah.
Thank you.
It's a wonderful framework. There is one thing I have to comment about, which is that I don't believe you've included the idea of an exact dot product in any of your analysis. And as soon as you do that, you'll discover that there's a big restriction on which systems can make a practical hardware of actually having a quire, that is, being able to do exact dot products with a small number of bits.
Right. That's a good point. I would think that this framework is actually being orthogonal to that particular issue, right?
Mhm.
Because it's just about the representation of the numbers themselves.
Right.
How you do arithmetic on it is something that we haven't dealt with at all.
Yeah.
And I think all these representations could potentially fit into that, but with the caveat that some of them would require very, very large quires to actually
Yes.
implement.
Yeah, I played with some of these other representations, and I always gave up trying to figure out how to do the dot product. That's one reason that type 2 units, I stopped working on them and went to type 3, for which I could do an exact dot product.
Right.
All right, we're getting into the tea break time, so let's thank our speaker again.
For any other questions, I'll be available out there.